Hi class, I want to work through all the problems that were on the Gateway exam. Also, if you look on your syllabus, today is the first day that you can take the Gateway exam in the resource room, or in the testing center, I mean, in the basement of Burnett. You might want to take advantage of that opportunity this week. Try to get this thing done with as soon as possible, but I want to go through several of the answers here. Many of you scored pretty well on the Gateway exam the first time through. Many of you passed. There were a lot of people that scored like 5, 6, or 7, and I think with clearing up just a couple of problems, you should be able to pass the exam the next time. So the first problem here is the derivative of e to the cosine divided by 8v squared plus 1. In this picture I see quotient rule. Quotient rule says take the derivative of the numerator, so we're going to get e to the cosine of v, and then there's also going to be chain rule applied in here. The derivative of cosine is negative sine, and then so that's the derivative of the numerator times the denominator, 8v squared plus 1, minus the numerator, e to the cosine of v, times the derivative of the denominator, 16v, and then all of that divided by 8v squared plus 1 squared. Right? And then just leave your answer like that. Okay, the next problem was quite a bit more involved. This is going to be chain rule several times. And I see there's a cosine function, there's a natural log function, and there's a quadratic function. So we're going to start from the outside. Take the derivative of cosine is negative sine. Right? And then the stuff on the inside we leave alone is natural log of z squared minus 8z plus 1. Right, then we take the derivative of natural log. The derivative of natural log is 1 divided by whatever we're taking the log of, so z squared minus 8z plus 1. Right, and then I got to take the derivative of what's inside there, which is just 2z minus 8. Okay, so if you see 3 different functions, you should end up with 3 different functions in your answer. There's this one, there's this one, and there's this one. Okay, the next one is, I see a product rule in here, and within that product rule I see some more chain rule. So take the derivative of the first, that's going to give me negative 48v, and I got to decrease the power by 1, so it's going to give me negative 9, not negative 7. And then I'm going to multiply that by the other function, cosine of 5v. And then I'm going to add to that the first function, 6v to the negative 8 minus 4 times the derivative of the second is negative sine of 5v and then times 5. All right, and then also, if you're taking this online, if you leave it like this, the computer's going to think about this as being subtraction. So make sure that you put the parentheses in there that are appropriate. I was a little bit more forgiving when I graded these by hand, but the computer is not going to be forgiving about that, and it's going to think about that as being subtraction. Okay, next one. Again, I see quotient rule, and within the quotient rule I see a chain rule. So the derivative of the numerator is secant squared of 3y, and then times the derivative of 3y is 3, times the denominator, 9y squared plus 7, minus the numerator, tangent of 3y, times the derivative of the bottom is 18y, and then all that divided by the denominator, 9y squared plus 7, quantity squared. Okay, the next one, this one's a little bit easier. This is, I see 3 functions in here. Many of you missed one of the 3 functions, but we're going to end up with the derivative of e to a power is just e to the power. And then I got to take the derivative of the power is negative sine of 3t. And then I got one more application of the chain rule, and that's going to be multiply that by 3. Okay, and again, make sure you put the parentheses around the negative sign so it's not thinking of that as being subtraction. Okay, next page. This one was kind of a mess. We got a quotient rule, and within the quotient rule we've got product rule, and within the product rule we have chain rule. So let's look at the big picture and say quotient rule says take the derivative of the numerator. The derivative of the numerator is going to be, well, it's a product, so it's going to be the product rule. So derivative of y to the cubed, or y cubed, is 3y squared times the cosine of 5y plus y to the third times negative sine of 5y times 5. So far all of that is the derivative of the numerator. We multiply that by the denominator, and we subtract the numerator times the derivative of the denominator, and then divide all of that by y to the third plus 1 squared. Alright, so that one is quite involved. Okay, the next one, the derivative of this is going to be, this is fairly straightforward. There's a little bit of chain rule here, but we're going to take the derivative of the first is 6x to the fifth times the second function e to the cosine of x times the derivative of cosine is negative sine of x, and then plus the first function x to the sixth minus 4. Oops, I messed that up, didn't I? Sorry. First function, derivative 6x to the fifth. Multiply that by the second function, e to the cosine of x. Then I add the first function, x to the sixth minus 4, times the derivative of e to the cosine is e to the cosine of x times negative sine of x. Okay, not this way. Alright, next one is kind of a mess also. We've got a function raised to the 7th power, and then the function on the inside ends up being a product and a sum. So we'll take care of the raising to the 7th power first. This is going to be 7u to the 6th sine of u plus 3 natural log of u raised to the 6th power. Then I work on the inside. The derivative of this is going to be the product rule. 6u to the 5th sine u plus u to the 6th times cosine of u plus, and then this one is, you could use the quotient or the product rule on this one, but this is really just a constant multiple of natural log of u, so just 3 times 1 divided by u, and that's it. Okay, you can also write this as 3 divided by u. Okay, and then number 9 was the implicit differentiation problem. These are the ones that we did on Wednesday. So I'm going to take the derivative of both sides with respect to x, but I'm going to think about y as being a function of x. So the first thing I'm going to do is write this as sine of x to the 6th plus f of x to the 6th equals x to the 3rd. Then the derivative of sine is cosine of x to the 6th plus f of x to the 6th. Okay, and then the derivative of what's inside is 6x to the 5th plus the derivative of this is going to be 6f of x to the 5th power times f prime of x. Okay, so that's chain rule on the left side, and then the other side is 3x squared. Alright, so the rest of this is just going to be a matter of solving for f prime. So this is multiplication. So I'm going to divide both sides by this. So we're going to end up with 6x to the 5th plus, all right, and I'm going to go ahead and substitute in the y's here. So this is going to be plus 6y to the 5th times f prime of x equals 3x squared divided by cosine of x to the 6th plus y to the 6th. Alright, then I'm going to subtract this, so we're going to get that minus 6x to the 5th, so this term will be gone. And then I'm going to take all of that and divide by 6y to the 5th. Alright, so my answer is going to look kind of messy, but it's 3x squared over cosine of x to the 6th plus y to the 6th minus 6x to the 5th, and then all of that divided by 6y to the 5th. All right, and then don't worry about simplifying that at all. Okay, then the last one, it seemed like a lot of people forgot how to take the derivative of arc sine. All right, so 5 arc sine is 1 divided by square root 1 minus y squared, and then the derivative of 2 to the y is natural log of 2 times 2 to the y, and then the derivative of 3 is just going to be equal to 0. Okay, so hopefully that clears up some of the problems that you had on this. It seems like if you go back and look at which problems or which type of rule for derivatives you end up running into a lot in this test is the chain rule. And the chain rule is going to show up time and time again. So make sure that you get that chain rule down, and if you need more practice, you can go to the end of chapter 3. I think it's on page 168. There's a whole slew of functions there that you can take derivatives of, and then the odd answers are in the back of the book. So just make sure that when you look up those odd answers in the back of the book that you realize that they're going to simplify the answers quite a bit. Okay, I want to also talk about section 3.10 and a little bit more about section 3.9 with the linear approximations. So I've got a couple of notes on that should get you through those homework problems from 3.9 and also 3.10. And then for sure I'll take questions on those when I get back. So in section 3.9, we talked about finding linear approximations to functions. And one of the problems that we looked at was, well, the idea was that to find a linear approximation, we said the linear approximation L of x evaluated near x equals a was f of a plus f prime of a times x minus a. All right, and so the idea was that if you had some kind of a function like this, let's say y equals f of x, and then you had some point down here, let's say x is equal to a, and the function looks like that, L of x is going to be just nothing more than the tangent line. Okay, so, and the idea is that when you are close to x equals a, this function f of x and L of x are almost the same thing. Okay, so nothing more than the tangent line. This is just another way of finding the equation of a tangent line. All right, so one of the things that we did in class was we said approximate the square root of 9.3. All right, and so we said we're trying to approximate the function f of x equals the square root of x, and we said near x equals 9. And the reason we're picking 9 is pretty close to 9.3, and also it's easy to plug into the function. All right, so according to our formula up here, L of x is going to be equal to the function evaluated at 9 plus the derivative of the function evaluated at 9 times x, which is 9, x minus a, which is 9, so x minus 9. All right, so really all we get to do is find this and plug in. So f of x was x to the 1/2 power, or the square root of x. So f evaluated at 9 is just the square root of 9, which is 3. The derivative is going to be 1/2 x to the negative 1/2, which is the same thing as 1 over 2 square root of x. And so f prime evaluated at 9 is going to be 1 over 2 times 3, or 1 over 6. Okay, so then all I got to do is plug those in, and we're going to end up with the linearization of this function is going to be f of 9 is 3, plus f prime is 1/6, and then x minus 9. And I'm just going to leave it in that form. All right, so then the question was approximate square root of 9.3. So square root of 9.3 is going to be approximately equal to L of 9.3, which is 3 plus 1/6. 9.3 minus 9 gives me 3 plus 1/6 of 0.3, which is going to give me 3.05. Okay, this ends up giving me 0.05. Okay, so that's my approximation. All right, then we talked about what this looked like graphically, and we said that this approximation was not exactly the same thing as the square root of 9.3. All right, and what we did was we said, here is what the function looks like. The square root of x looks something like this. We're going to go out here to 9, and we're trying to approximate what is the square root of 9.3. All right, so we're trying to find out what's the value of the function at 9.3. All right, hang on one sec. I got to plug in my computer. Okay, so what we found was L of x was basically the equation of the tangent line, and we'll just say that this is L of x. We're trying to approximate the y value here, but we found the y value here. All right, and so our function, or square root of 9.3, is actually going to be a little bit less than 3.05. All right, and what I'm interested in knowing is something about how much less. All right, so one of the things we should know is that there's going to be an over approximation here, and the reason that there's an under approximation here with 3.05, and the reason that there's an under approximation is the shape of this curve. This graph is concave downward. All right, and the downward concavity is really going to be dependent upon the second derivative of the function. All right, so when we talk about the error, we're talking about how far these 2 points are apart. So if I say this is the error, and the error is really going to be dependent upon how big this number is. Okay, and so let's think of that as an error that is a function of x. As we move away from that point of tangency, that error typically is going to get bigger. All right, so what I'd like to be able to do is talk about, well, how big is the error at that point? This is something that we didn't talk about much, or we didn't talk about at all when we talked about these linear approximations, but there's a formula in the book that you don't need to worry about deriving it, but understand what it's dependent upon, and it's really dependent upon a couple of things. It's going to be dependent upon the second derivative of the function at x. Okay, and then it's also going to be dependent upon how far x and a are away from each other, and it's actually going to be the square of that difference. And then one other thing is that we're going to take that second derivative and just divide it by 2. All right, and then the error is going to be the absolute value of that number. All right, and I should say this is approximately equal to the error. All right, so the bigger the second derivative and the more curvature there's going to be on that graph, the further these two things are going to be apart. And then also, the bigger this difference is, the further we move away, the bigger the error is going to be as well. All right, so if we go back and we say, well, what is the approximate error in finding the square root of 9.3? All right, we can say that the error then of x is going to be approximately equal to the second derivative. All right, now remember the function was x to the 1/2. The first derivative was 1/2 x to the negative 1/2. The second derivative is going to be negative 1/4 x to the negative 3/2. All right, so this f double prime of x, and we're looking at what is that at x equals 9, we're going to end up with negative 1/4 times 9 to the minus 3/2 divided by 2, and then 9.3 minus 9 squared. All right, and then when you simplify all this, you're going to find that this error is 0.004167. Okay, so we're saying that the error is going to be, that's a pretty small number. Those two numbers were really pretty close together. All right, then if I really want to know what is the exact error, I could just say, well, the exact error is going to be equal to 3.05 was our approximation minus the actual value of square root of 9.3. And then I plugged this into my calculator, and I ended up getting just 0.4099. All right, and so the idea is that this error that we get from this formula is almost the same thing as the actual error. All right, that's not nearly as important as being able to find the local linearization and use it to approximate the value of a function, but I think there might be one or two questions where you're asked to find what is the approximate error, and that's the way that you're going to be intended to do that. Okay, so the next thing I'd like to look at is section 3.10, and 3.10 is about some theorems having to do with functions that are continuous and differentiable. All right, so 3.10 is theorems about differentiable functions. Okay, and the first theorem that's in this section is called the mean value theorem. Okay, and the mean value theorem says this. It says that if f is continuous, on an interval, let's say from a to b, and f is differentiable on the interval from a to b. All right, and then here we're including the two endpoints on the continuity, and we're including only the interior points for the differentiability. Then the theorem says this: there exists some number c on the interval from a to b such that the derivative at c is equal to f evaluated at b minus f evaluated at a, all divided by b minus a. All right, now this is what the theorem is saying in pictures. We've got a function that is continuous, right? And the hypothesis on this one is the continuous and differentiable function. Function is continuous. Remember, that means there's no holes, no jumps, no asymptotes. And differentiable means it's a smooth function that doesn't have any sharp corners. Okay, so this is going to be a function that's a nice, smooth, continuous function over an interval from a to b. All right, so if we draw some kind of a function like that, let's say this is a and this is b, there's going to be some point here, and there's going to be some point, let's say, up here, and let's say that this function does something like this. Okay, some kind of a function that doesn't have any holes, jumps, or asymptotes, and is smooth between a and b. All right, so if we look at the left-hand side of this equation, the right-hand side of the equation, the f of b minus f of a, right, that just represents the distance, the vertical distance between these 2 points. So this is f of b minus f of a. And then the denominator, just b minus a, is the distance between these. So b minus a. So when we talk about this ratio, we're talking about the change in y divided by the change in x. All that is the slope of this line. Okay, so this side of the equation is just slope of that line that goes through those 2 points. Okay, then on the right hand side of the equation we have f prime of c, right? And f prime of c is just the derivative of the function at some value c, right? And it says that these two slopes are going to be equal to each other, so it looks to me like there's going to be some value of c that happens right about here, where the tangent line, that tangent line, is parallel to this line that goes through those 2 points. Okay, so the theorem says that if the conditions are met, if the function is continuous and differentiable, that there is going to be some point in between a and b where the slope of the tangent line is equal to the slope of the secant line. Okay, now a typical kind of question on this one might be, given a function, find the value of c. All right, so let's say that we have f of x is equal to x squared minus 4x plus 5. And we want to find the value of c which satisfies the mean value theorem, and I'm just going to abbreviate that with MVT. So the function is this: find the value of c which satisfies the mean value theorem on the interval, let's say from 1 to 4. Okay, so the theorem says this, that there's going to be some value of the function, the derivative, that's going to be equal to f evaluated at 4 minus f evaluated at 1 divided by 4 minus 1. Okay, so I'm going to work on the right-hand side first. If I take 4 and plug it into this function, we're going to get 16 minus 16 plus 5. That's 5. And if I plug in 1, we're going to get 1 minus 4 plus 5. That's going to give me 2. So we end up with 5 minus 2 divided by 3. And so we get 1. All right, now on the other side of the equation, we have the derivative. All right, so the derivative is 2x minus 4. All right, now I want to know for what value of c that this is going to be true, so all I'm going to do is say, well, 2 times whatever c happens to be minus 4 has to be equal to 1. So 2c is going to be equal to 5, c is going to be equal to 2.5. Okay, so the value of 2.5 is the value that makes that the conclusion of the mean value theorem true. All right, so let me show you graphically what this represents. All right, so here's the graph of the function. F of x is equal to x squared minus 4x plus 5. We're interested in what happens from 1 to 4, so I'm just going to come up here and grab a point and put it on the graph at x equals 1. And then I'm going to take another point and put it on the graph at x equals 4. Okay? And then I'm just going to connect those 2 points with a line segment. And so we get that. All right, so we said that the right-hand side of that equation was f of 4 minus f of 1 divided by 3. That's the slope of this line segment, which is, looks like, is 1. All right, then I'm going to do one other thing. I'm going to take another point and just put it on the graph. And I'm going to tell the software to draw me the tangent line to this graph at this point. All right, so that dotted line that you see is the derivative, or the slope is the derivative. And then if I just grab that point and move it until I end up with that dotted line being parallel to that secant line, and it looks to me like that happens right about there or so. Okay, so if you look at what happens here, the x coordinate at that point is 2.5. Right, and that's exactly what our work indicated as well. So we go back here and see that that happens at c equals 2.5. There's a point where the derivative is, or where the tangent line is parallel to the secant line. Okay, let's try another one. Suppose that our function this time is the square root function. So f of x is square root of x. And I want to find the value of c that satisfies the conclusion of the mean value theorem on the interval from 0 to 4. Okay, so first of all, I guess that I didn't mention that we know that this function is continuous. It's a parabola, and we know that any kind of a polynomial function is continuous. And then also, the derivative of that function ends up just being equal to 2x minus 4, which is also defined everywhere between 1 and 4. So the two conditions here, continuous and differentiable, are satisfied. Okay, so for this one, first thing is, if I want to check the conditions, the graph of this function is a square root function. And between 0 and 4, this function is a nice, connected, smooth function. All right, then if we look at the derivative of this function is 1 half x to the negative 1 half, so is this. All right, but if you look at what happens on this function, at x equals 0, this thing is going to be undefined. Right? This is one of those cases where we don't really care about what happens there because we're just saying that it has to be differentiable on the interior, just between a and b, not necessarily at a and b. All right, so our conditions are going to be met on this one. So now we want to find out where is the derivative going to be equal to f evaluated at 4 minus f evaluated at 0 divided by 4 minus 0. All right, so the plugging in here, we're going to get the square root of 4 is 2. The square root of 0 is 0. We're going to divide that by 4 minus 0, and we're going to end up with 1 half. Okay, and then on this side, we're going to get the derivative. The derivative we've already said was 1 divided by 2 square root of x, and we want to know what's going to make this a true statement. So 1 divided by 2 square root of c is going to be equal to 1 half. All right, so if I cross multiply on this, we're going to get 2 square root of c is equal to 2. If I divide both sides by 2, square root of c is going to be equal to 1. C is going to be equal to 1. All right, so again, we're going to end up with the line that goes between these 2 points. That has a slope of 1 half. If we go over here to 1, we're going to find that the tangent line at that point also has a slope of 1 half, and this line are going to be parallel to each other. Okay, so let me again demonstrate that on GeoGebra. All right, so let me turn that function off, and we'll get rid of these points. And we'll turn on the square root function. We're going to put a point at the origin. And we're going to put another point at 4, 2. We're going to draw a line segment through those 2 points. We're going to put another point on the graph. And we're going to tell it to make a tangent line to this graph at this point. All right, and then if I just drag this point C around a little bit and make the line steeper, we're going to find that by the time we get over here to x equals 1, that's the point where those 2 lines are going to be parallel to each other. Okay, so next one. Let's see if we can make this a little bit messier. So suppose that we have another function, and suppose that that function is f of x is equal to x to the third minus x squared plus 2. And I want to know for what values of x is this going to, or is the mean value theorem going to be satisfied between -1 and +2. All right, again, this is a third-degree polynomial function. All polynomial functions are continuous and differentiable everywhere, so our conditions are going to be met for this one. So the theorem just says that there's going to be some value between -1 and 2 where the derivative is equal to the function evaluated at 2 minus the function evaluated at -1 divided by 2 minus -1. All right, so if I take 2 and plug it into this function, we're going to get, what, 8 minus 4 is 4 plus 2 more is 6. F of -1 is going to give me -1 minus 1 plus 2, that's 0. And then we're going to divide that by 3. And so the slope of the line that goes through those 2 points is going to be equal to 2. The derivative of this function is 3x squared minus 2x. And so we want to know where is 3c squared minus 2c equal to 2. All right, so if we move the 2 over, we're going to get 3c squared minus 2c minus 2 is equal to 0. Okay, this function doesn't factor at all. So my next choice then is going to be use the quadratic formula. All right, so using the quadratic formula, I'm going to find that c, or maybe I should have called this x, is going to be equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So negative b is going to be negative negative 2, or 2, plus or minus b squared is going to give me 4, minus 4 times a is 3, times negative 2. Divided by 2 times 3 is going to give me 6. Okay, so we're going to get 2 plus or minus the square root 4, and then this is going to give me plus 12 times 2 is 24. This is going to give me 4 plus 24 is 28, all divided by 6. All right, so we're going to end up getting two values. One is 2 plus the square root of 28 divided by 6, and the other one is going to be 2 minus the square root of 28 divided by 6. And let me just tell you that when you plug in or evaluate these as decimals, you're going to get that one value is about negative 0.548, and the other value is going to be about 1.215. Okay, those are the two values that you're going to get when you just simplify those expressions. Okay, so let's go back to GeoGebra and see how this shows up as graphically. All right, so let me clear up this mess again, get rid of all those, and we'll turn this function off. We'll turn this one on. All right, so there's the graph of the function. Again, I'm going to plot 2 points. One of those was at negative 1, so it looks like negative 1, 0. And then the other point was at x equals 2, so it looks like up here at 2, 6. All right, and then I'm going to connect those two with a line segment. And so it looks like that slope ends up being equal to 2, which is what we came up with on our paper. And now the question is, where is the tangent line going to have a slope of 2? So if I go back over here and say, let's draw the tangent line. Whoops, I need to put a point on the graph first. So we put a point on the graph, and we tell it, I want to find the equation or the tangent line to that graph at that point. Right, and right there at that point, that looks like it's almost close to being parallel to my other line. Right, now, if I just grab that point and move it slightly, it looks like, I guess that's maybe a little bit closer. All right, so it looks like right there is one of my answers. And if you look over here, the coordinates of point C end up being about negative 0.55. Right, and if you go back to what we found out on the paper, we found that that was going to be true at negative 0.548. All right, so it looks like there's one of the answers. And then if I keep moving this line across here, we end up with, there's another place right over here where that looks to me like it is parallel to this line as well. And that happens at about x is equal to 1.2. And on our paper, we found that that was actually 1.215. All right, so we actually end up with two places where this is going to be true. All right, now, if you go back to the mean value theorem, okay, this is something that a lot of times in everyday language we think exists means that there is one. All right, well, actually, it just means that there is going to be at least one for which this is true. And in the last example, we found out that was going to happen at those two values. So there's actually two answers where the derivative is equal to the slope of the secant line. Okay, one last one I want to go through with the mean value theorem. And that is, suppose our function is f of x is equal to 1 divided by x minus 1. And I'm interested in finding the value that satisfies the conclusion of the mean value theorem on the interval from from 0 to 2. All right, so if we proceed on this one the same way that we did on the other ones, we're going to end up with f prime of c is equal to f evaluated at 2 minus f evaluated at 0 divided by 2 minus 0. The right-hand side of this equation is going to be 1 divided by 2 minus 1, that's 1, minus what I get when I plug 0 in there, When I plug 0 in, we're going to get 1 divided by -1, so that's -1, and then divide that by 2 minus 0. All right, so you're going to get 2 divided by 2, that's 1. And then the derivative of this, if we think of that as x minus 1 to the minus 1 power, the derivative of that's going to be negative x minus 1 to the negative 2. And then if you apply the chain rule, the derivative of x is just going to be equal to 1. So we're going to end up with negative 1 divided by x minus 1 squared. And we want to know, where is that equal to 1? All right, so really if we put c in there like we've done before, so c minus 1 squared equals 1. All right, if I cross multiply, I'm going to get c minus 1 quantity squared is equal to -1. All right, then if I try to solve this by, let's say, taking the square root of both sides, we're going to get c minus 1 here, but over here we're going to get the square root of -1, which there isn't a real number that satisfies that. Right, you could say that that's equal to I, but we're not going to be really concerned about imaginary numbers and finding those numbers here because that number I really is not in the interval from 0 to 2. All right, so it looks to me like this fails on this particular problem. All right, but I think if we go back and if we look at the graph of this, I think we should be able to kind of figure out what the problem is. All right, so if we go back to GeoGebra, I'm going to get rid of all this garbage, and we'll turn that function off, and we'll turn this one on. And if we proceed the same way that we did before, we said let's put a point here at x equals 0, and another point at x equals 2, and we draw the secant line between those two. All right, so the slope of that line is 1, and then if I plot a point on the graph, and I say give me the derivative of that function at this point, right, and then I take that point and we move it. Right, so now we're looking for a place where the slope of the tangent line is equal to the slope of the secant line. Right, and if you look at here, this ends up getting more and more negative, and then this gets more and more negative again, and I don't ever find a place where that dotted line is going to be parallel to the secant line. Okay, so what's the problem? Well, if we go back to the theorem said if f is continuous on the interval from a to b, all right, so there is a problem here. That function is not continuous when x is equal to 1. Right? When x is equal to 1, there's an asymptote. All right, so if the hypothesis isn't satisfied, the conclusion isn't necessarily satisfied either. All right, so this isn't a failure of the mean value theorem. This is actually just saying, you know what, this function is undefined somewhere in this interval, and therefore the conclusion is not necessarily going to be satisfied. Okay, so there's not anything wrong with this. It's just saying that if the hypothesis isn't met, the conclusion might not be met either. Okay, so let me go through one other type of problem using the mean value theorem. And this one might be something that would be an application in real life. That when you're driving down some interstates in other states, they have toll booths where you have to stop and pay for a toll. And so let's say that you're at this toll booth at, we'll say 12 noon. And let's say that these toll booths are 60 miles apart. Okay? So you come through this toll booth, they stamp your ticket, they know that it's 12 o'clock when you hit that toll booth, and then let's say that along this road the speed limit is equal to 60 miles per hour. Okay, so if you're driving the speed limit, you should get here at 1 o'clock. But let's say you get here at 12:50. Okay, now I'm going to also tell you that there's a policeman sitting right here who is clocking you as you come through here, and as you're coming up to that toll booth, he sees that you're slowing down. He never saw you going more than 60 miles an hour. There's another cop that's sitting right here, and he's also clocking you as you come in here, and he sees that you're going less than 60 miles an hour. All right, but they don't see you anywhere from like here up to this point. All right, so let's say that you did this, and you you hit this toll booth at noon, you hit this toll booth at 12:50, and this cop over here, he turns on his sirens and he pulls you over and gives you a ticket. All right, so I want to know, why is he justified in giving you a ticket if he never saw you going more than 60 miles an hour? All right, and maybe I should say, what does this have to do with the mean value theorem? All right, so the idea is that if you're speeding anywhere along here, you're eligible to get a ticket, but nobody actually saw you speeding. All right, so if we apply the mean value theorem, first of all, let's say that S of t is the position at time t. Okay, so we'll say that we'll say t equals 0 here. So S of 0 is going to be equal to 0. And we'll say that S of 50 minutes later is going to be equal to 60 miles. Okay, so then if we talk about the derivative of that, the derivative of the position is going to be the velocity. All right, so the mean value theorem then says that there's going to be some place in between 0 and 50 where S prime of t is equal to S evaluated at 50 minus S evaluated at 0 divided by 50 minus 0. All right, so this side of the equation is going to give me, what did we say, 60 minus 0 divided by 50 minus 0. That's going to give me 1 1/5. That's 1.2. All right, now this 1.2 is what? Miles per minute. All right, if I want to change 1.2 miles per minute, I can just multiply that by 60, and that's going to give me 72 miles per hour. Okay, so 72 miles per hour, someplace has to be equal to the velocity. Okay, so someplace the velocity was 72 miles an hour. And so his argument is that if your average velocity, this, was equal to 72 miles an hour, that means that someplace you had to be going 72 miles an hour. And your argument is, nobody ever saw me going that fast. Okay, well, if he pulls out his calculus book and says the mean value theorem says that you were, maybe you want to make an argument also and say, well, the hypothesis of the mean value theorem isn't satisfied. Okay, and he says, all right, well, show me how that's not satisfied. And so you say, well, maybe my function isn't continuous. All right, so what would that mean? Suppose you're driving down the road, and let's say you start out here at 0, and you are moving along here, and then here's some value of t, we'll call it t star, where your position is not continuous. All right, so let's say that you did something like this. All right, and so he's probably going to laugh at you and say, well, there's no way that this could possibly happen. All right, so why is that true? Why is that impossible to happen? All right, well, if you think about it, you're going to be moving down the road here, and you're going to be, let's say, so far away from the first toll booth. And then instantaneously, you're going to be like teleported down the road someplace further down the road. Okay, well, teleportation doesn't apply on this stretch of highway. Okay, so that argument is going to be void. All right, so then if you said, well, maybe my position function isn't differentiable. Okay, so what does that mean? All right, well, if it's not differentiable, that means that maybe something like this happened. You're going down the road, and then your velocity function instantaneously changed, something like that. All right, so if you want to make that argument, then you're saying that, well, my velocity function then is some number like this, and then instantaneously it's going to change to some other value. All right, so he may also argue with that and say, you know, you're saying that your velocity can instantaneously change from one number to another number, and that doesn't happen. Okay, you can't instantaneously change your velocity. Okay, the velocity function is actually going to be a continuous function as well. All right, so because your position function is continuous and your position function is differentiable, his argument is valid that someplace along the way you had to be going 72 miles an hour. Right. And in fact, there was probably some places that we were going more than 72 miles an hour because you were clocked at going slower speeds here and here, which means that you were probably going faster than 72 miles an hour someplace along that path. Okay, so that's just kind of an application of the mean value theorem. It is a theorem that ends up getting used quite a bit to make some different arguments. All right, there's a couple of other arguments, or a couple of other theorems in this section as well that we've already mentioned a little bit about. And the first one is, suppose that f is continuous on an interval from a to b, and f is differentiable on the interval from a to b on the interior. Okay, so the same hypothesis as the last one, or as the mean value theorem, but this one says, then suppose also that f prime of x is positive for all x on the interval from a to b. All right, so the function is continuous and differentiable. All right, so what conclusion can we make from there? This is one that we talked about before. We're going to say then the function f is increasing on the interval from a to b. All right, so if the derivative is everywhere positive, the function is increasing. Okay? And then there's a second bullet on this one that says, what if the derivative is greater than or equal to 0 for all x on AB? All right, so now we're just saying not just positive, but also can possibly be 0. Then the conclusion, we're going to say, well, we can't really say it's increasing because some places the derivative might be 0. We're going to say then f is non-decreasing on the interval from a to b. Right? So non-decreasing just means that it's never going downhill. Okay, so this is called just the increasing function theorem. Okay, the increasing function theorem. And that's something that we've already talked about. So if we want to know where is a function going to be increasing or at least non-decreasing, we just take the derivative and find out where it's positive. So let's say that we've got a function like f of x, let's say is equal to x squared minus 4x plus 1. And the question is, find an interval where this function is increasing. All right, so we just want to know where is the derivative going to be greater than, let's say, greater than or equal to 0. All right, so the derivative of this function is just going to give me 2x minus 4. If I say greater than or equal to 0, 2x has got to be greater than or equal to 4. X has got to be greater than or equal to 2. So anywhere where the value of x is bigger than or equal to 2, this function is going to be increasing. And I think you'd also make the argument that any place else, the function is going to be decreasing. Okay, so this function is going to be increasing on any interval that is to the right of 2. Okay, another theorem that we talked a little bit about, and in fact we did this when we were graphing the derivatives, is suppose that f is continuous on the interval from a to b, and f is differentiable on the interval from a to b. And then the theorem says if f prime of x is equal to 0 for all x on the interval from a to b, then what conclusion can we make? All right, it says the function is continuous and differentiable on a to b, and the derivative is everywhere equal to 0. All right, well, that tells me that the function f of x must be a constant. Okay, f of x must be a constant function. So it must be like a function like f of x is equal to like 4. Okay, just a horizontal graph. Okay, and again, because of the stuff that we've talked about before, I think this is a fairly straightforward kind of a problem. This is called the constant function theorem. Constant function theorem. Okay, there's one other theorem that's in this section that is kind of interesting. It's one that we're going to end up using a little bit in order to prove that one function maybe is bigger than another function. All right, and the theorem says this: suppose that g and h are continuous. And we'll say that they're continuous on the interval from a to b and differentiable on the open interval from a to b. And suppose that g prime of x is less than or equal to h prime of x for all x on the interval from a to b. And g of a is equal to h of a. Okay, so this is the first part of this. We've got two functions that are continuous and differentiable. All right, so there's no holes, no jumps, no asymptotes, no sharp corners. And suppose that g prime is less than h prime for all x on the interval from a to b. And g of a is equal to h of a. All right, so let's see what this might look like. All right, so we've got some number here a, and we've got some number over here b. All right, and it says that, first of all, let's say this: g of a and h of a are the same. All right, so let's say that they're both equal to this value. All right, then we've got this idea that g prime is less than or equal to h prime. All right, so that tells me how fast the function is increasing or decreasing. This says that if these are both functions that are increasing, that means that the derivative of h has got to be more than the derivative of g. All right, so let's say that the h goes something like this. The slope of that is going to end up being equal to h prime. And then g prime is less than that, so g prime might increase like this. Okay, so the theorem says this, that they're going to start out at the same point. If this is h and this is g, and h has a bigger derivative than g does, then what we want to do is make some conclusion about where do they end. All right, so if g prime is less than h prime, for all x on the interval from a to b, and this is true, then my conclusion is that h of b must be bigger than or equal to g of b. In other words, this point has to be higher than this point. All right, and that seems kind of obvious, that if this function is steeper than this one, this is going to end at a higher point than this one does. Okay, now the second part of this one is, suppose that g prime of x is less than or equal to h prime of x, like it was up here, for all x on the interval from a to b, and we'll say g of b is bigger than h of b. All right, so now we've got kind of that same picture. We've got these two functions are going from a to b, but now we're saying that sorry, these are going to be equal to each other. All right, so now g of b is equal to h of b, so that tells me that they're going to end at the same point. All right, we're saying that g prime is less than h prime. All right, so again, h is going to do something like this. and g is going to be less steep. So g must do something like this. And so then we want to say something about the beginning points. All right, so if these two things are equal to each other at the end, and g prime is less than h prime, then that means that g of a would have to be bigger than or equal to h evaluated at a. All right, so again, we're just talking about how fast these functions are increasing or decreasing. This theorem is actually called the racetrack principle. Okay, the racetrack principle, here's the idea. If we say these are two horses, they start at the same place, and horse H is faster than horse G throughout the entire race, who's going to win? Okay, horse H is going to win. Okay, whereas the second part of this one says, suppose that there's a dead heat, they tied, but all the way through the race, horse H was faster than horse G. Okay, so what had to happen during the race? Well, if they tied and horse H is faster than horse G, that means that horse H was coming from behind, which means that horse H was behind horse G throughout the entire race. Okay, so again, the racetrack principle is just going to give me a way to compare two functions. All right, so let me give you an application of that. Suppose that we're interested in two functions. Let's say f of x is e to the x, and let's say that g of x is equal to 1 plus x. Okay, and the question here is, for, let's say, x between 0 and, I don't know, 5, which function is bigger? All right, so if you think about this, we could just plug in numbers and see which one's going to be bigger, but I think that we've got an infinite number of points that we'd have to plug in. All right, so what I'd like to do is try to apply the racetrack principle here and see if we can come up with an answer. All right, so what I want to look at then is the fact that f evaluated at 0 and g evaluated at 0. F evaluated at 0 is going to be e to the 0 is 1, and g evaluated at 0 is going to be 1 plus 0, which is 1. All right, so these two functions are going to start at the same place. Okay, then I want to look at, what about f prime of x? F prime of x is e to the x, and g prime of x is equal to 1. All right, so now, if I want to compare these two things, f of x and g of x prime, all right, if we think about what happens if you plug in any number in here that's between 0 and 5. So e to the first power is 1, e to the second is like 2.718 squared. That's going to be bigger than 1, and so on. So you're going to find out that as long as x is a number between 0 and 5, that this derivative is going to be bigger. Okay, so what does that tell me then? We've got these two functions that start at the same place. They look like this. One function, g of x, is a linear function that goes something like this. And f of x is another function that goes through the same point, but it goes something like this. Okay, so which function is going to be bigger? Well, because they start at the same place, and the derivative of f is bigger than the derivative of g, by the racetrack principle, f is going to always be bigger than g. Okay, all right. So it seems like, you know, kind of a, I don't know, it's a kind of a weird way to prove something, but it is something that you're going to use in order to prove that two functions are going to compare in such a way as that. Okay, so that should get you through section 3.9, talking about the errors, and then also 3.10, which is talking about differentiable functions, which is going to involve the mean value theorem. It's going to involve the racetrack principle. It's going to involve the increasing function theorem, and then also the constant function theorem. Right, those are all kind of important theorems, and that are going to be used a little bit later on. But they're important to know. The other thing that's important is to really concentrate on the hypotheses of those, because some of the questions in the homework ask you whether or not it's justified to say some kind of a conclusion. You've got to go back and make sure that you check the conditions. Okay, so while I'm gone, please take advantage of the testing center. I put the your first shot at the Gateway exam on Blackboard. If you don't have an 8 or better, you need to make sure that you get into the testing room and get that taken care of. And then if you do have an 8 or better, then you are done with the Gateway exam. You don't need to do anything else. All right, so hopefully you'll take advantage of the time that I'm gone to get in and get that Gateway exam taken online. So you should be working on section 3.9 and 3.10 for Wednesday night. And hope you guys all have a nice day, and I'll talk to you on Wednesday. All right, thanks. Bye.